and welcome this Friday morning to Math 95. The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mail. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I'll respond as soon as I can. All righty, so today we're going to take a look at section 6.4. I just want to remind you of, I have an office hour that's 1:15 to 2:15, and the Math Center hours are listed there along with the Zoom ID number. So if you want to contact them. And with that, we're going to go ahead and start on section 6.4. So the last, actually 3 days, we've been looking at factoring trinomials. On Tuesday, we looked at factoring trinomials that had a leading coefficient of a 1. And then Wednesday and Thursday, we looked at 2 different methods of factoring trinomials that had a leading coefficient of something other than a 1. But the whole focus was on trinomials. Today, we're going to be looking at some trinomials and then also some binomials. But first of all, the trinomials, we're going to talk about perfect squares. What is a perfect square? Well, with arithmetic, a perfect square is a number that is the product of 2 identical positive factors. So for instance, 0 times 0, which is 0 squared, equals 0. So 0 is a perfect square. 1 times 1 equals 1 squared equals 1. So 1 is a perfect square. Not very interesting, but how about 2? 2 times 2, which is 2 squared, equals 4. 4 is a perfect square. 3 times 3, 3 squared is 9. 9 is a perfect square. 4 times 4, or 4 squared equals 16. What, 25, 36, 49, 64, etc. These are all perfect squares because they have 2 identical factors. Well, in terms of a polynomial, let's say you've got x squared plus 6x plus 9. And we go through and factor that, and we get x plus 3 times x plus 3. So we could, in fact, if we wanted to, write it this way. So this is a perfect square trinomial because it has 2 identical factors, 2 identical binomial factors. And you could also write this like that, okay? But again, this is called a perfect square trinomial. Now, I'm going to look at some characteristics of perfect square trinomials. So let's go back to this x plus 3 times x plus 3. And if we FOIL it all out, we get x squared plus 6x plus 9. Let's say we take x plus, oh wait, hold on. We take x minus 3 times x minus 3. If we FOIL that together, we get x squared minus 3x plus 9, x squared minus 6x plus 9. Okay, let's say we take 2x plus 5 times 2x plus 5. We get 4x squared plus 10x plus 10x plus 25, combining like terms, 4x squared plus 20x plus 25. And finally, let's do, how about y minus 7 times y minus 7. So we get y squared minus 7y plus 49, combine like terms. That looks too much like an x. Y squared minus 14y plus 49. I basically wanted to get a bunch of examples down there to look at. Now there's a pattern. Let's look at these answers, okay? So those answers, those are all perfect square trinomials because they all came from 2 identical factors, okay? Notice that in each case, the first term is a square. The last term is a square. and there is a plus sign in front of the last term, okay? So here are some characteristics of perfect square trinomials. The first term has to be a perfect square, or just a square, whichever. The last term has to be a square, and there needs to be a plus sign in front of it. Now, so you're in terms of FOIL, first times first, x times x, you're multiplying the same numbers together, so you should get a square. Last times last, you're multiplying the same numbers together, so you should get a square. But also consider this, plus times plus is plus, but minus times minus is also plus. Again, minus times minus is also plus. Now, there are more characteristics to this, but I'm not going to go into the details because I've determined it's more work to see if it's that or not than to just go with this. So what I tend to tell students is if you're given a trinomial and you're trying to determine could it be a perfect square, look at the first term, look at the last term, look at the sign in front of the last term. If you've got a square in front, a square at the rear, and a plus sign, then it might be a perfect square, and you go on and test it further. If it doesn't meet all three of those criteria, it is not a perfect square. And we'll look at that some more here as we go along. Okay, so let's see here. How about this? X squared plus 14x plus 49. Is this a perfect square trinomial? Well, x squared is a perfect square, or just even a square. 49 is a square, and there's a plus sign there. So far it looks good, but let's determine whether it is. If it's a perfect square trinomial, it has two identical factors. Well, going back to section 6.2, we would break it apart, x and x. If the two factors are going to be equal, how would you have to break apart the 49? With a 7 and a 7, right? That's the only, okay. But it would have to be plus. Does that give me plus 14x in the middle? 7x plus 7x? Yes, it does. So yes, this is a perfect square trinomial. All right. How about this one? X squared plus, let's see, 9x plus 16. Okay. It has a square in the front, a square at the rear, and a plus sign, so it could be, let's see, it would have to be x, and what, 4 and 4, and plus and plus. Does that give me 9x in the middle? No, it gives me 8x. So this is not a perfect square there, trinomial. Now, it might still be factorable, but it's not a perfect square. Why is it nice if we can, if something's a perfect square? Because then you know the factors are identical, so it's less work, okay? To factor it, that is. All right, now, let's take a look at this problem. X squared plus 10x plus 25. It says to factor it, okay? So again, the emphasis here is on seeing if it's a perfect square. If it is, factoring it that way. If it isn't, going back to a previous section. Well, we'd have to split up the x squared. We'd have to split up the 25 to get a plus 10x plus plus. Is that correct? Does that give us 10x in the middle? Yes, it does. So you could write it that way, or you could write it this way. Okay. And again, either way is correct. Okay, let's take a look at this one. 121 plus 4x squared plus 44x. Is this a perfect square? Well, what's the first thing I need to do with this before I start messing with it further? Anybody? Any ideas? There's something wrong with it.
You got to rewrite the order.
Exactly. Good job. So it would be 4x squared plus 44x plus 121. Now, This is a trinomial that has a leading coefficient other than a 1. So if I'm going to factor it by the normal procedure, I've either got to use grouping or trial and check, both of which take a while. But let's see if it's a perfect square trinomial. 4x squared would get split up 2x and 2x, right? 121 would get split up 11 and 11, and they'd have to both be positive. Does that give me 44x in the middle? Yes, it does. So 2x plus 11 times 2x plus 11, or 2x plus 11, the quantity squared. That was much quicker than using the other methods. Okay, so again, take a little time, see if it's a perfect square. Then if it's not, you got to go on and factor it, one of the previous methods we discussed. Okay, let's see here. How about this one? 9x squared minus 48xy plus 64y squared. This trinomial is in standard form in terms of the variable x. It has x squared in the first term, x to the first power in the second term, and no x in the third term. So it is in standard form. The leading term is a square, the final term is a square, and there's a plus sign in front of it. So 9x squared would be 3x and 3x. That's how you'd pull it apart. 64y squared would be 8y and 8y. Okay. And then, oh, but the middle is negative, isn't it? So we'd have to have a minus sign in both cases, wouldn't we? Okay. So let's see if that gives me minus 48xy in the middle. Does it? That's minus 24xy. That's minus 24xy. So yes, it does. So I could write it this way, or I could write it like that. Any questions on that example? All right. So in dealing, eventually what's going to happen here, in fact, I think that's, let's see, Monday, after so today we're focusing on a couple of things. And Monday, it's going to be kind of a free-for-all, and that the assignment will say, okay, we've looked at taking out the greatest common factor, factoring by grouping, factoring trinomials this way and that way, factoring different, what we're going to call perfect square trinomials, and then something we're going to look at here now called the difference of two squares. And they're going to be randomly thrown together there. And so we're going to have a checklist, but we're not there quite yet. That'll be Monday. Okay. So here we're dealing with perfect square trinomials, 3 terms. What about a binomial, a polynomial with just 2 terms? For instance, x squared minus 49. Okay. So it's not a trinomial. So the things we've looked at 6.2 and 6.3 do not apply. Okay. But consider this. What if I take, in fact, let's come back to this. Let's just forget that for a moment. What if I have x plus 3 times x minus 3? And I FOIL that together. I get x squared minus 3x plus 3x minus 9. When I go to combine like terms, these 2 middle terms cancel each other out, and I'm left with that. Okay, let's look at another example. Let's say I've got y plus 7 times y minus 7. When I multiply them together, I get y squared minus 7y plus 7y minus 49. When I combine like terms, the middle 2 terms cancel each other out, and I've got y squared minus 49. This is a binomial. Not only is it a binomial, but it is a difference, as in subtraction, of 2 squares, because this is x squared minus 3 squared. Now, we wouldn't, if we were foiling this together, we wouldn't write it like that. But my point is, can you see that this could be written as x squared minus 3 squared. So this is the difference of two squares. So is this y squared minus 7 squared. Okay. Now, sorry, my phone is buzzing off the wall. It's distracting me. I need to put it over there. This is also the difference of two squares. But notice something about their factors. You've got the sum of two numbers times the difference of two numbers. And what are those two numbers? They're the bases of the squares. They're the bases, that's supposed to be a y, of the squares. So what is all that telling you? Okay. Let's say we have the following problem. We have w squared minus 64. And I want to factor this thing, okay? Because it's a binomial and there's no greatest common factor, the question I would ask myself is, could I write that in this form? Well, the answer is yes. W squared could be written as w squared, and 64 could be written as 8 squared. Now, these two numbers are going to show up in the factored answer. I'm going to have the sum of those two numbers times the difference of those two numbers. That will be the factorization of this binomial. So if it's the difference of two squares, then I can factor it this way. Okay, this isn't the factoring process. This is saying, identifying, yes, it fits the pattern, so we can go to this, or no, it doesn't fit the pattern, so we got to try something else. Okay. I say that because I'll have students that'll think that this is factoring and then they'll stop. No, that's factoring the individual terms maybe, but it's not even that. Okay. Let's see here. H squared minus 144. That is a difference. H squared is H squared. 144 is 12 squared. So my factors are the sum of the two bases times the difference of the two bases. This situation right here is called conjugate pairs. So the sum of two numbers times the difference of the same two numbers in the same order is called conjugate pairs. Okay. If you're in Yakima, you also know about Bartlett pairs and D'Angelo pairs, but these are conjugate pairs. They aren't as tasty. All right. Are you okay with this problem? Okay. What about this one? X squared minus 27. That is a binomial. It's got a subtraction sign. Let's see. Well, 27, the square root of 27 isn't a nice number, is it? So basically, we would say, no, this is not the difference of two squares. It doesn't factor under nice numbers, okay? So we don't factor it. We would say it is prime. Okay, now, what about this one? 49 minus w squared. This is a binomial. There's no greatest common factor. Now, it's not in standard form. When you are factoring trinomials or larger than trinomials, like quadrinomials, quintrinomials, whatever, standard form is important. With a binomial, standard form isn't as important as the difference of two squares. And let me show you. I'm going to leave it like it is, and then I'm going to say, oh, can I write it in this form? 7w, 7 plus w, 7 minus w. And that is a correct answer. Okay, that's the easy way out. Now, if you want to go the long way, you could do this. You could say, well, that would be the same thing as negative w squared plus 49. Let's factor out a 1. So now we get w squared minus 49 inside. And then we get negative 1, w plus 7, w minus 7, and we get that answer. This is the same as that answer, but it took longer and it's a little more complicated. Let me convince you. W plus 7 is equal to 7 plus W, right? Addition's commutative. If I take this -1 and I distribute it, I'd get negative W plus 7, and that's negative W plus 7, 7 plus negative W, okay? So again, something like this, rather than putting it in standard form and going through all of that, just factor it as it is. But if it's a trinomial or larger, standard form is usually pretty important to do first. Okay. Oh, what about this one? X squared plus 64. Is that the difference of two squares? No, it's not the difference of anything. It's the sum of two squares. Well, let's see. Would that be x plus 8 times x plus 8? No, because that would be x squared plus 16x plus 64, because there's that middle term. Well, maybe it's x minus 8 times x minus 8. Well, that's going to be x squared minus 16x plus 64. Well, how about x plus 8 times x minus 8? Well, that's going to be x squared minus 6. This is prime. Okay. Now, I almost want to make this statement. I almost want to say, well, the sum of two squares doesn't factor. But let's be careful. Consider this. Is that the sum of two squares? Yes, it is. Does it factor? Yes, it does. I can take out the greatest common factor. Now, what's left here doesn't factor any further, but I did factor it. So let me say it this way. Once you have removed any greatest common factor, if what you have left is the sum of two squares, then that does not factor any further. This is not a prime polynomial, though, because I did factor it. This piece doesn't factor any further, but because I factored it, taking out the greatest common factor, it's not a prime polynomial. It's only prime if you can't do anything to it. So be careful with that. I saw there were some questions yesterday students were asking, and that's the mistake they were making. It's like, oh, and it wasn't in this section, it was with the trinomials, but it's like they had something like this, and this part didn't factor anymore. So they wrote prime, and the WebAssign said, no, that's incorrect. Well, they had factored out the greatest common factor. So that was the answer right there. Okay. All right. What about this? X to the 4th minus 81. That's a binomial. It's in standard form. Not that I'm concerned about it, but it's in the form of the difference. Oh, what's the square root of x to the 4th? X squared. The square root of 81 is 9. So in other words, x to the 4th is x squared, and 81 is 9 squared. Okay, so here's my two bases. So I'm going to get the sum of the two bases times the difference of two bases. Okay. I don't know if any of you are old enough to remember the TV show called Lamb Chops. It was about a lady who had a puppet that was a lamb. I know this is really stretching back there, obscure. The theme song from that show. Anybody? This is the song that never ends, and it goes on and on. You ever heard that? The song that never ends? What does that have to do with this problem? Well, this is the polynomial that appears that it never ends, because we're not done yet. Why not? Well, this thing here is the sum of two squares, and it doesn't factor any further. But this thing is the difference of two squares. So it factors further. Now the song's over. Thank goodness. Okay. So you always want to make sure, am I done? Have I factored it as far as I can? Let me give you sort of a arithmetic equivalent, okay? And then I'll come back to this one in just a minute if you didn't get it all written down. But let's say I've got, 4. And I factor that, prime factorization, 2 times 2, okay? But let's say I've got 8. No, not 8, 12, okay? Well, 12 is 2 times 6. I factored it, but am I done? No, because the 6 breaks apart further. So sure, I pulled out a prime factor, but I can keep going. So here, yes, this becomes this, but this factors further. And don't just leave this as your answer. You got to bring this piece along, even though you can't do anything else with it. You got to bring it along for the ride because it's part of the final answer. This whole thing multiplied back together should give me that. All right. Okay. Let's see here. How about this? This is a binomial. Is it the difference of 2 squares? Well, 2a squared isn't really a nice number squared, is it? 200. Oh, so it's not the difference of 2 squares yet. What do I need to do first? Take out the greatest common factor. Okay, now we've got a squared minus 10b squared. So we get 2 times a plus 10b times, I shouldn't have such a big space there, and then times a minus 10b. Okay. Oh, look, here's a binomial that's a difference, but it's not the difference of 2 squares. So here's my final answer. But again, if there's a greatest common factor, whether it's a binomial or a trinomial or whatever, you want to take that out first. I can't think of a single example where taking it out first is going to be a bad thing, but I can think of lots of examples. Here's one right there that if you don't take out the greatest common factor, you're going to say, oh, it's not the difference of 2 squares, it's prime, and you're wrong. So be careful. Oh, I shouldn't say you're wrong. That's harsh. And you're not quite correct. There, is that softer? Okay. All right. How about this one? 20x squared minus 5. Is that the difference of 2 squares? Well, first of all, there's a greatest common factor. So let's take that out. Oh, now we've got what? 2x and 1. So 5, 2x plus 1, 2x minus 1. Now, a couple of things I want to clarify. When I'm writing my 2 factors, I always do the plus first, but you could just as well do the minus first, because remember, multiplication is commutative. So you can do it that way if you want. It's not a big deal. Okay. The other thing is, I get a lot of students that don't want to do that step I just erased. They just want to go straight to the answer. And that's fine, except here's a common mistake that I see. They didn't think about the fact that this whole thing gets split up. So this has got to be a 2 and this has got to be a 2. So my thinking is this. If I say put it into that form, hopefully it'll get you thinking more about that this has got to be a 2x, not a 4x. Okay. So if you skip this step and you don't get these right, don't blame me. I tried to warn you. All right. Let's see, care about this one. Y to the 4th minus 625. That's a binomial. It's got a subtraction sign in the middle. Y to the fourth would be y squared, squared. 625, is that a perfect square? It is. If you're not sure, tell you what, do the square root on your calculator. Let's see. The square root of 625 is, oh, it's 25. Yeah, 25 times 25. So be careful. So I'm going to get y squared plus 25, y squared minus 25. But we aren't through yet, because the first factor, the sum of two squares, doesn't factor further, but the second factor, y squared minus 25, is y squared minus 5 squared. So y plus 5, y minus 5. This is the song that never ends. Okay, sorry. We good to go on that? Okay. Here's a good one. M to the fourth, n to the fourth, minus 16. It's a binomial. It's got a subtraction sign. Let's see if I can write it this way. Well, this would be what? M squared, n squared, and 4 squared. So I'm going to have m squared, n squared plus 4, m squared, n squared minus 4. There was a famous baseball player. His name was Yogi Berra, not Yogi Bear. He's the guy that went around with Boo Boo and said, "Hey, another picnic basket from Ranger Smith." Remember that guy? Okay. Yogi Berra, baseball player, he said, "It ain't over till it's over." Well, this ain't over, folks. Why not? Because this is also the difference of two squares. So my final answer is going to be that. Okay. Let's see here. Now they're going to mix them up. So some of these are going to be binomials that will or won't be a perfect square, or a difference of two squares, excuse me. Some of them are going to be trinomials that will be a perfect square trinomial. So let's see here. S squared t squared minus 20 st plus 100. This is a trinomial, and it's in standard form, whether you choose s as a variable or t. In fact, I would argue let's call the variable st, because we've got st to the second power, and then st, and then no st at all. Okay. But it has a leading coefficient of a 1. So this actually goes all the way back to section 6.2. So we're not going to have to use grouping or the trial and check. We're just going to use this and say, well, the product is 100. The sum is negative 20. How about negative 10 and negative 10? Okay. Oh, you know what I overlooked? I could have done that maybe even in less work. This looks like it might be a perfect square. Starts with a square, ends with a square, and there's a plus sign there. Well, how would you break up 100? 10 and 10, but it's got to be negative, and there we go. So that actually is not much faster than what I did, but again, I sort of forgot. We're looking for perfect squares. Okay. How about this one? 2p to the fourth minus 32q to the fourth. Well, this is not a trinomial, so it's not a perfect square trinomial. It's a binomial. So now we're looking for the difference of two squares. And it's not yet. What do we need to do? Take out the greatest common factor. Just like that. But then this would be p squared minus, and then 4q squared. P squared squared is p to the fourth. 4q squared squared is 16q to the fourth. Okay, so I get 2 times p squared plus 4q squared, p squared minus 4q squared. But wait, there's more, because this is also the difference of two squares. It's p squared minus 2q, the quantity squared. So we've got 2 times p squared plus 4q squared times p plus 2q times p minus 2q. Again, it just goes on and on and on. All righty. Any questions there? Let's see here. How about this one? 49z squared minus 14z plus 1. This is a trinomial. Is it a perfect square trinomial? Well, the first term is a perfect square. The last term is a perfect square, and there's a plus sign, so it's looking good. Let's find out. 7z, 1. 7z, 1. Would it be plus plus or minus minus? How are you going to get a minus 14? It's going to have to be minus minus, right? So let's see if that works. 49z squared minus 7z minus 7z plus 1. 49z squared minus 14z plus 1. Ka-ching, ka-ching. Okay, so that was a perfect square. What if it wasn't? Well, then we'd try factoring it using grouping or trial and check, those methods. But it's quickest to try seeing if it's a perfect square first. Okay. Okay, how about this one? Is that a binomial or a oh, it's a binomial, isn't it? Okay, it's a binomial. Is there a greatest common factor? Nope. Is it the difference of two squares? It's not the difference of anything, is it? So it's prime. Okay, how about this one? 3a squared minus 4a minus 4. This is a trinomial. It's in standard form. There's no greatest common factor. Oh, but you know what? The first term isn't a square. The last term is a square, but it's got a subtraction sign in front of it. So of those 3 things I wanted you to test for, only one of them is good. So it is not a perfect square. Okay, fine. It doesn't have a leading coefficient of a 1 either. So we're going to have to factor this trinomial with a leading coefficient other than a 1. Oh, I forgot to ask you. So after yesterday, when you've now used the grouping method and the trial and check method, did you have a preference? Doesn't matter if you didn't, but I'm just curious, did anybody come up with a preference of the two that wants to? Okay, well, all right. Which method would you like me to use on this one? Do you want me to use that grouping ABCPS method or the trial and check method?
Let's do grouping.
Grouping? Grouping it is. Okay. A is 3, B is -4, C is -4. The product is -12, and the sum is -4. How about -6 and 2? Okay, so I get 3a squared minus 6a plus 2a minus 4. Factor by grouping. Greatest common factor of the first 2 terms, 3a, leftover is a minus 2. So the leftovers are a minus 2, and looking up here, I'm going to have a plus 2. So a minus 2, 3a plus 2, and there you go. Does anybody else that's out there want me to do it the trial and check method? Okay, then I won't. Any questions about this one? Okay, let's see here. 20 in s squared minus 60 in u plus 100 n. This is a trinomial. Standard form's a little bit fuzzy there, isn't it? Is there a greatest common factor?
Uh, 20.
Okay, 20. Anything else? Look at the variables.
Oh, and
Good. So 20n, so we'll take that out, gives us s squared minus 3u plus 5. There's no way we're going to be able to factor s squared minus 3u plus 5 because we've got different variables, you know, and you could have, if it was like s squared minus 3 us plus, 14 u squared, something like that, where you've got s squared and u squared and su in the middle, or us, but this isn't going to factor any further. Now, is it prime? No, it's that. Okay. All right, how about this one? A squared minus 4ab minus 12b squared. This is a trinomial. Is it a perfect square? Well, a squared is a square, but 12b squared is not, and it doesn't have a positive sign in front of it. So it's not a perfect square. But the leading coefficient is a 1. So I'm going to split it up that way. Oh, and I'm going to split the b's up at the end, right? So my product is -12 and my sum is -4. Those are the same two numbers we had earlier on a problem. I don't have to do the grouping though, right? If this coefficient is a 1, when I find those two numbers, they go right in to the answer. Don't waste your time doing things you don't have to do, okay? One of the criticisms I got in the past from some of my colleagues for teaching this grouping method is that students going on to pre-calc would, or not this grouping method, but the grouping method, we didn't use it here, but they'll take a polynomial that's like this, that they should be able to factor easily, and they'll use grouping on it, because grouping works for all of them, but it's a waste of a lot of extra work, and they didn't like that. So be careful. Don't do more than you have to. Be efficient. All right. Well, I think I've tortured you enough for today. So over the weekend, 6.4, and let's look at what's coming up here. So Monday, we're going to do 6.6, Tuesday, 6.7, Wednesday, 6.8 in the chapter review. Thursday, we're going to review on Zoom. So your first test is coming up a week from today, okay? Just to kind of let you know what's coming up in the future. So I'm going to stop the recording.